Good evening, everyone, or good morning or good afternoon, depending on whenever you are listening to this. But hope you are all doing well. Today, I'm going to talk about how large language models are being used in information retrieval. And what we're going to do is look at how search has evolved. We're going to examine the neural architectures being used, and we're also going to discuss challenges that are still being worked on. Let me start with some history because I think it helps explain why we needed neural IR approaches. So in the 90s, search engines like Alta Vista just matched keywords, right? They look up which documents contained your search terms. So like if you searched laptop overheating, but a document within what they were searching for said computer temperature problems, it wouldn't find anything on it, even though it's the same thing, right? Because it's doing simple keyword matching. In the 2000s, that brought smarter ranking with Google's PageRank, which used links or link structure to find authoritative pages. Then machine learning helped learn from user behavior, but we were still like stuck with that same issue, like matching keywords first, right? So in the 2010s, gave us word to vec, which learned that car and automobile are similar by representing words as vectors. Finally, we had semantic similarity at the word level. So because car and automobile are completely different words, it is still able to understand that they are, um, similar. They pretty much mean the same thing, right? Then 2018 brought BERT and transformers. This is absolutely revolutionary. BERT uses context to understand meaning. Like bank in Riverbank is going to get a completely different representation than bank in Money in the Bank. Now we can match by meaning, not just keywords. Here's why this matters. Let's say we were searching climate change impact on farming. Keyword methods find those exact words, but they would miss a paper that would be titled like anthropogenic warming effects on crop yields, even though it's the same concept, right? This vocabulary mismatch is like the central challenge in information retrieval. Neural information retrieval solves it by putting queries and documents in a shared vector space where similar meanings are close together regardless of the words used. What is an LLM? So, a large language model, or an LLM, is a neural network trained on massive amounts of internet text. It learns by predicting missing words you show. So, like, let's say you show it the cat sat on the blank, and it guesses what goes there. After billions of examples, it learns grammars, facts, semantic relationships. So, like, an option could be like mat or on the floor, and it just predicts it, predicts the missing word based off billions of examples. Obviously, that's a nuanced example. It's not a correct answer, but that's just kind of how the concept works. So the key innovation here is bidirectional context. BERT looks at all the surrounding words to understand meaning in it, right? In the bank charging fees, it needs to see charging and fees to know that this is about a financial institution, not a riverbank, right? So the contextual understanding is perfect for semantic search. Two steps turn text into vectors. First, tokenization breaks text into subwords using byte pair encoding. This handles new words and works across languages. So unhappiness becomes un and happiness, which helps the model understand word structure. Second, embeddings. Each token becomes a 768 dimensional vector. The model processes these through transformer layers, where tokens look at each other through self-attention and build context-aware representations. We measure similarity with something called cosine similarity, which is just essentially the angle between vectors. Similar vectors mean similar meanings, even with different words. There are two main types of architectures. Bioencoders, they process queries and documents separately. You pre-compute all document vectors ahead of time and then just encode the query and do fast similarity search. So with algorithms like, FAISS, you can search millions of documents in seconds. Cross encoders process query and documents together, not separately. They do them together. And letting them interact through attention, right? That's their methodology. And this is more accurate, but way too slow for large scale search, since you'd have to run the model on every document pair. Real systems use both in like a two-stage pipeline. Bioencoder retrieves top 100 candidates quickly, then cross-encoder re-ranks them accurately. That's kind of what Google uses. Training uses contrastive learning. Pull relevant pairs together, push irrelevant pairs apart. That's kind of like the idea here. The key is choosing negatives, I think. Random negatives are too easy. In-batch negatives use other documents in your training batch, efficient and harder to distinguish. Hard negatives are the most powerful. You use keyword-based methods to find the documents that match words but aren't semantically relevant. Like for laptop overheating solutions, a hard negative might be laptop cooling parts for sale. Same keywords, different meaning, and this is what teaches the model to focus on semantics, not just keywords. We evaluate with MRR for first result position and NDCG for overall ranking quality. Three key papers shaped the field, in my opinion. Dense passage retrieval from 2020 showed neural methods could beat traditional keyword search, which was a major breakthrough. Colbert introduced late interaction, keeping token level vectors and doing fine-grained matching, which is more accurate than basic bioencoders, but faster than cross-encoders. ANCE improved training by continuously mining hard negatives during training. These form the foundation of modern neural information retrieval. Hybrid retrieval, the best of both worlds. So the important insight here, keyword and neural methods aren't competing, they're complementary. So traditional methods like BM25 excel at exact matches, specific product models, error codes, technical terms. Neural methods at semantic queries where people use different words for the same concept. The best approach is going to combine both. Reciprocal rank fusion is popular. It combines rankings from both systems based on position, not raw scores. So on the BIR benchmark, testing 18 domains, keywords alone get 0.45, neural alone gets 0.48, but a hybrid of them gets 0.52. The hybrid consistently wins because when one struggles, the other is able to compensate. So a real customer support, or a real example, customer support, customer asks, my subscription won't renew, please help. The old system would search for subscription, renew, and then it would find some generic billing FAQ. I'm sure we've all had like a similar experience, right? Maybe not with this exact thing, but just something like that, right? So the LLM system, what it does instead of the old system, it understands payment issue plus auto renewal failure, which is like crazy to think about based off the old methodologies. It would struggle to even find that that's what the user is essentially looking for. It predefines it, or it defines it into clear categories, so it is able to retrieve the information. So then from there it finds failed payment troubleshooting, and then it's going to provide a step-by-step payment update instructions plus the phone number for billing issues and sources cited. So that's kind of like the secret sauce nowadays. That is like what is the trend, and that is what's working. That is the new wave. Let's talk about RAG. RAG stands for Retrieval Augmented Generation. It combines with answer generation. So the 3 steps are retrieve relevant documents, add them to the prompt as context, then a language model generates an answer with citations. This solves hallucination. When models confidently make up wrong answers, that's what hallucination is, right? So, like for example, it may say LeBron James won his first NBA title in 2007, but that's actually when that's when he competed in his first NBA title, not when he won. He actually won in 2012. So RAG is what grounds generation in real retrieved documents. So it basically makes these answers more verifiable and accurate. And this is the standard for QA systems, research assistants, customer support, where accuracy really matters. RAG has 3 components. The retriever finds relevant documents, could be DRR or DPR, Colbert, or a hybrid. The augmenter, which formats them into a prompt, and the generator, typically a model like T5, produces the answer. For training, you can freeze the retriever and just train the generator. Do expensive end-to-end training or alternate between updating each. Variants like Fusion and Decoder and Self-RAG optimize for different objectives, but all share the core idea of grounding generation in retrieved evidence. So some classic benchmarks: MS Marco with 500,000 real search queries. Another benchmark, BEIR. This tests zero-shot generalization across 18 domains like medical, financial, scientific, legal, and more. Results are revealing. Neural methods only beat keywords by 3 points on average, and actually do worse on some domains. So this is why generalization is difficult, and why hybrid approaches are most robust, and that's what is the focus nowadays, really. 3 main challenges remain. First, domain adoption. Models trained on web search don't transfer well to specialized domains with limited training data. Second, efficiency. Searching billions of documents requires fast approximate algorithms and model compression to meet latency requirements. Third, interpretability. We can't explain why one document ranks above another, which limits trust in high-stake applications. Emerging directions include multimodal retrieval across text and images using models like CLIP and conversational search that handles multi-turn dialogues. Key takeaways. Main points to remember are informational retrieval solves vocabulary mismatch by matching meanings instead of keywords. Biencoders give speed, cross-encoders give accuracy. Two-stage pipeline gives both. Hard negatives are crucial for training. Hybrid systems consistently outperform because keyword and neural methods are complementary. That is the main takeaway that I found in my research. It's the hybrid way. um, that is the most optimal way, right? It's not always, it's not like a black and white thing. That's what I've seen. Um, and another thing I'd like to say is RAG, grounds generation, and retrieval to reduce hallucination. Um, and the challenges that remain are in like domain adaptation, efficiency, and interpretability. And yeah, that's pretty much it. Feel free to reach out with any questions on the topic, or if you would like to discuss some of these ideas in general. I think I would really enjoy that. I'd enjoy that conversation. I'd enjoy to learn more from you, or just expand on this conversation, because I do think that this is a very important time for AI, and just working in corporate, this is kind of like one of the biggest applications. Document intelligence, information retrieval, setting up RAG chatbots for certain policies within the company. So, I think this is very important to stay on top of, and I think it is important as someone who's trying to dive deeper into technology to try your best to read up on some of these concepts. And I think it's very interesting. It may not be interesting to everyone, but yeah, I just think it's a very exciting time to be in the tech industry, and to work in AI. So yeah, if if you ever want to connect, please feel free to message me, leave a comment, anything like that. And um, other than that, thank you for taking the time to listen to this presentation on large language models, information retrieval, um, AI, whatever you want to call this presentation. But yeah, thank you so much, and I hope you enjoy the rest of your day.